In Python world, package management is complicated and inconsistent. This is the question posted on Hacker News 2 years ago. And this is what people were saying in response. Instead of solving dependencies, pip just starts installing stuff. Python packaging is a mess for some weird reason that baffles me. Whenever there is native code involved, things can get tricky. There is no fast path out of this mess. When I started my deep dive into Python packaging, I've stumbled upon more and more confusing questions. What is the difference between sdists, eggs, and wheels? Why pip has the break system packages option? Why the official Python packaging user guide suggests you need to always use pip like this? What package managers have to do with Sudoku? Why poetry and pip sometimes get stuck for unbelievably long time trying to resolve dependencies? Why you cannot pip install anything when building a Docker image based on Debian bookworm? And why there is a flurry of new experimental Python package managers all written in Rust? And the deeper I explored, the more packaging seemed absolutely at odds with Python philosophy. There should be one, and preferably only one, obvious way to do it. I had no choice but to test 11 different Python package managers, from very popular to experimental, to understand how Python community tries to find the one tool to rule them all. In this episode, I'm sharing all the answers that will make you more advanced in Python packaging than probably 80% of your teammates. This means being able to figure out why dependencies installation for your project fails and how to fix it, what are the different means of distribution of your Python code, and how to deploy your Python application in a safe and predictable way, regardless if you use containers or not. But before I start, if you are really serious about Python, try Python track on Codecrafters. This is not yet another educational platform where you have a bunch of isolated coding exercises, or even worse, where you just follow what a lecturer types on a screen. Codecrafters is not like that, because both of these approaches simply do not work. When it comes to professional programming, learning the craft means training a whole lot of things. Analyzing requirements, reading APIs documentation, making design choices and actually implementing them in a context which is as close to the real work context as possible. This is how Codecrafters work. You choose a project, for example, build your own Redis or build your own DNS, and then you go implement it piece by reading the requirements for a current stage, writing code in your favorite code editor, running the tests, and pushing changes to a special Git repository. Rinse and repeat. Check the video description for an affiliate link to Codecrafters. If you or your company buys a subscription by following my link, not only will you have a chance to become a stronger software engineer, you will also tip me so that I can spend more time on quality videos for this channel. To understand the current state of Python packaging ecosystem, we need to look back in the past and start from the very beginning. Python appeared in 1991, and at that time package managers didn't exist as an idea. It was 4 years before dpkg appeared in Debian and 5 years before CPAN, the comprehensive Perl archive network, came online. If you needed a library, you had two choices. First, you could write it from scratch by yourself, or you could try to find someone else's work on some FTP server, download an archive, extract it, read installation instructions in some README file, and if the package contains C extension code, possibly compile that code. And of course, in the end you had to put all the files in the right places where Python would find them. Every library, therefore, was a unique artifact. It goes without saying that in this period of Python history, sharing code was hard and using shared code was even harder. These were the times when mostly the approach of C programming language dominated in Python community. You need a function, you write it. Just think how different it is from the present time. Today a package manager is a commodity, and typically you don't think twice before checking for third-party code online. Now let's fast forward to the year 2000. Python 2.0 was released, and in its standard library there was a new package called distutils. Distutils is no doubt a legend. It has come a long way and was retired just recently. You won't find distutils in Python 3.12. Distutils was the first attempt in Python history to come up with a standard for packaging Python code. The idea was to have something like a makefile from C world, an entry point for package-related tasks, a cookbook with a set of well-known recipes to build and install packages. As a library author, you would write a file that looked somewhat like this. You would then run python setup.py as dist to produce a package, which was called as dist for software distribution, which you could then upload to some FTP server or to your own website. As the library user, you would download the package archive, extract it, and run python setup.py install. If a package is Python-only code, setup.py will simply put package files in the right places. If a package contains extension code, setup.py will first run a compiler and then copy resulting binaries in other files. With distutils, package installation became so much easier. There was no need anymore to tinker with compiler flags, no need to copy files manually. Files from Python packages, by the way, are copied to a special directory called site packages, and whenever you try to import a module, this directory is always scanned. Python knows about site packages because it's included in its sys.path list. Thanks to distutils, packages installation process got structured, but you still had to find packages in the first place, or at the very least there has to be a way to know that a certain package exists. In 2003, a new website called cheeseshop was established by members of Python community to share as dists. This is what we know as PyPy today. The number of Python packages grew, and with it a new problem became apparent. There was no way with distutils and setup.py to say that package X needs a package Y to work. There was simply no concept for package dependencies. Each package was still treated as a unique universe. That's why in 2004 another foundational Python packaging library was born, setuptools. Setuptools did not replace distutils, but instead extended it to support new features. Install requires statement now allowed to install libraries required at runtime, tests requires libraries required for testing, and setup requires libraries required to do the build itself. Setuptools supported as dist format, but also introduced a new one called egg. At least it made sense, not like with the cheeseshop. Python is a serpent, it lays eggs. Python egg is like a Java jar file. It is a zipped archive with the package code and accompanying metadata files inside. The main benefit of eggs was that all the package files after installation were contained in a separate package directory and not just dumped into site packages root as before. This meant that to uninstall a package you simply had to delete that separate package directory. In addition to that, Python could work with eggs even without extracting them, just like Java does with jars. Having all package files contained also meant that you could have several versions of the same library installed at the same time in your environment, because all what was needed for that to work is to different versions to use different directories. To make module imports work with eggs, Python had to find files in those site packages subdirectories. And this is how the problem was solved. When Python would check the site packages directory and there would be files with the pth extension, those files will be loaded and they were expected to add subdirectories of egg packages to sys.path. Setup tools not only introduced a new package format, but also the first Python package installer, Easy Install. You could use it to install an sdist or an egg package from the cheeseshop, the precursor of PyPy, or from a remote URL or from an already downloaded file. And of course, Easy Install would get package dependencies too, which was a huge improvement in development practices. There was a problem though. As the name suggested, Easy Install only supported one aspect of package management: installation. You could not list or remove installed packages. What was even worse, if a package installation was interrupted in the middle for any reason, Easy Install would leave your environment in a broken state. You had to do the cleanup by yourself before trying failed installation. In 4 years from Setup Tools' initial release in 2008, a better alternative to Easy Install was presented to the Python community. It was built on top of Setup Tools, so nothing existing was thrown away, but enhanced. Do you see the pattern already? This new tool was called pip, and to this day it is the default Python package manager. Not only did pip support packages removal, could list installed packages, handled interrupted installations better, it also had much better error messages than Easy Install. But the most interesting idea that pip brought to the Python world was the requirements files. You could write down all your project dependencies in a simple text file, conventionally named requirements.txt, one dependency per line. And then you could install them and their dependencies, of course, possibly on a different machine with a single pip command. Even cooler, you could get a list of all the already installed packages along with their exact versions and store those names and versions to requirements.txt. This would let you to recreate your particular Python environment even on a different machine. Pip and virtualenv were set to become a killer combo. A typical Python development environment setup now could look like this. And yet, even though pip coupled with virtual environments was a tremendous step towards developers' quality of life improvement, there were still serious traps yet to be experienced by thousands of Pythonistas. For one, you had to be disciplined enough not to call pip outside of a virtual environment. On a typical Linux or Mac OS system, there was typically a Python interpreter pre-installed, with some packages and some system tools written in Python, relying on those packages. So if you would think that installing packages globally in a system-wide location is a good idea, on a Red Hat-like Linux distribution you had good chances to break the default operating system package manager yum, for example. Pip developers tried to disarm this trap by introducing the --user command line option, which would install packages not in the system global site packages location, but somewhere in a user's home directory. This option signaled to pip users, do not run pip as root, do not install packages globally. At the same time, the --user option was a confirmation that pip will be probably often used outside of a virtual environment. And that was the real problem. Even though --user looked like a solution, it didn't protect you from a broken yum issue. Yes, you were not physically overwriting important system-level Python packages, but you could easily shadow them when your local version of a package took priority over a global one. This mess would get even worse if you'd happen to have more than one Python interpreter installed, because every time calling pip install you got to know which pip exactly you are calling and which Python will run it. This is why the official Python packaging documentation recommends to always use pip as a module, like this, python-m pip. If you do it and you know which Python you are calling, you then automatically know which pip you are calling. My recommendation, though, is straightforward. Always use virtual environments. If you keep forgetting to activate a virtualenv, please check my other video about command line tools that will help you automate typical project-related tasks, like a virtualenv activation when you enter a project directory. Another pip trap was related to sdists, distribution packages with C or C++ extension code that had to be compiled to a loadable binary library. In 2012, it became all the more apparent that pip and setup tools were simply not designed to handle installation of complex sdists. By this time, a community in community has formed, people that were doing scientific calculations using Python. For decades, scientific computations were a domain of a programming language specifically designed for such purpose by IBM in 1958. But what if you could take battle-proven Fortran libraries and wrap them in a package so that you will have all the power of the optimized machine code and nice readable syntax of a dynamic scripting language? That's how famous NumPy and SciPy packages came to life. Now more scientists could implement their ideas in code without the need to learn complex statically typed language from the times of punch cards. The problem was to actually set up a working Python development environment. Pip would not help you to install, let's say, a Fortran compiler to then build your Fortran libraries for scientific packages like NumPy or SciPy. Back in 2001, the NumPy project even forked distutils, the package building library, because distutils totally lacked any Fortran support. Maintainers of scientific packages had to come with a workaround after workaround to make things, well, work for them. And then in 2012, Google hosted a PyData workshop, which became really pivotal for the course of Python packaging. At the time, Guido van Rossum worked at Google, so he was of course invited to the meetup. During the workshop, 3 prominent contributors from the Python scientific community shared with the Python's benevolent dictator for life their frustrations with the existing Python packaging tools, to which Guido responded.
It really sounds like your guys' needs are so unusual compared to the larger Python community that you're just better off building your own.
And there was in fact a blessing for Conda to be born. Conda was a new package manager, not based on setup tools, which is, as you remember, in turn is based on distutils. Conda was instead written from scratch. How is it different from pip? To begin with, Conda always installs packages in so-called environments, and these are not virtualenvs, but more like what you get when you use Homebrew. All the relevant binaries and shared libraries are stored in one place, completely independent from your system-installed software. So yes, Conda not only manages Python packages, but everything around them. like the already mentioned Fortran libraries. Conda doesn't use PyPy, the Python packages index. It has its own repositories called channels. Channels only contain binary packages, so there are no sdists in Conda. From the very beginning, Conda was a part of a freemium Python distribution called Anaconda, and channels were controlled by the company that developed it. By the end of 2012, Conda repositories contained about 100 packages compiled for Linux, macOS, and Windows, and the numbers grew. Of course, the scientific Python community with time realized the risks of having important infrastructure reliant on a single private company. In 2024, you can install one of the community-maintained alternatives of Conda package manager, Mamba or Pixi. There is now also an independent package channel called Conda Forge. A more detailed review of Pixi comes in the later part of this video. Apart from solving the issue of building complex Python packages, Conda implemented another killer feature that was nowhere else to be found in Python world: dependencies solver. You see, dependencies of dependencies, the so-called transitive dependencies, can get into a conflict with each other. Let me explain with an example. Imagine your project depends on a library called HTTP client. HTTP client in turn depends on a library cookies, version 7 or higher. Your project also depends on another library, HTTP server, which needs cookies as well, version 2 or higher. Now there is a new HTTP client release, and its developers figured out that HTTP client doesn't work properly with cookies version higher than 7, so they cap their cookies dependency to be less than version 7. Now, when you try to upgrade your project dependencies to the latest available versions, it is the job of a dependency solver to find a combination of versions of HTTP client, HTTP server, and cookies that satisfy each other's requirements. For this particular and actually very simplistic example, it sounds like the solution is obvious. Upgrade HTTP client and HTTP server, but try not to upgrade cookies to a version higher than 7. In fact, there is another reasonable solution. Upgrade both HTTP server and cookies, but stay with an older version of HTTP client that did not yet introduce a cap for cookies. Or, your dependency solver can also reject an upgrade altogether with an error message saying there is a newer version of cookies available which is required by HTTP server, but I cannot install it because the new HTTP client blocks it by setting a version cap. Dependencies resolution is such a complex problem with no single right solution that people are writing papers on this topic. To make things even more fun, let me tell you that getting to know what are the dependencies of a particular package is also a challenge in Python world. More on that later. So yeah, Conda was the pioneer in the field of dependencies resolution for Python, because pip at that time didn't try to solve anything. It either installed new versions or failed. We will come back to the topic of dependencies resolution again in this video, as it is to this day still one of the crucial problems in Python package management. While Conda was a huge leap forward for the scientific community, its channels still contained just a selection of all the packages available on PyPy. So in general, for Python developers in 2012, package management issues still remained unsolved. Pip could still break your environment or even your operating system setup. Python core developers, of course, recognized the problems. First, in September 2012, the critical importance of virtual environments was confirmed with the addition of a new module to the standard library that shipped with Python 3.3. The module was called VENV. Although a separate virtualenv package still exists to this day and is mentioned in the official Python packaging guide, you won't see it being used much in the wild. VENV is now the de facto standard. Then, in February 2013, another standard was established. While egg format for Python packages was quite popular, it had no formal specification and its use was somewhat inconsistent. Wheels practically became a reincarnation of eggs, all the same zip archive with Python code and potentially also precompiled extensions. There were a couple of important differences though. both related to improved standardization. First of all, Wheels now only supported one single way to install packages. There was no more a Java-style installation option of just dropping an archived egg inside packages directory. With Wheels, you have to always extract package contents. Another thing which was tackled in Wheels was package file naming convention. Wheel file names always follow this schema. This, as you can see, is a package pre-built for macOS version 10.6 or higher, running on an Intel CPU with support for CPython interpreter of at least version 3.6. Support for CPython means that this particular package won't work on Jython, for example, a Python interpreter for Java virtual machine. The story is actually a bit more complex on Linux, which may be useful to know if you deploy Python applications to production, either using containers or not. There are many different Linux distributions that ship different versions of the standard C library, glibc. Practically everything written in C or C++, including Python extensions, rely on glibc and is compiled against a certain glibc version. So if an extension is compiled against glibc 2.17, it will work on a more modern glibc 2.18, but will fail on a system with an older glibc, say version 2.5. That is why Wheels support several different so-called many Linux tags, which indicate the minimum supported glibc version. For example, packages with many Linux 1 tag are based on the glibc version 2.5 from the very old CentOS 5.11. These packages will work even on the oldest systems. Many Linux 2014 builds are based on glibc 2.17 from CentOS 7, so packages with this tag will work on any Linux distribution with glibc 2.17 or higher. In practice, you shouldn't worry about many Linux tags, but keep in mind that if you plan to deploy your Python application on a system which is older than CentOS 5.11, expect no pre-built binary packages for it. Same goes for distributions that do not use glibc but instead ship with alternative implementations like Muscle. There will be no pre-built binary packages for Alpine or the Muscle version of Void Linux. Your package manager on such systems will be trying to compile extensions, which, as you now know, can be a real pain when it comes to scientific packages. The two changes from 2012 and 2013, the env module incorporation into the standard library and Wheels format specification, made Python packaging much more structured, which was very important for reproducible builds. In my opinion, we should thank Conda with its mandatory environments and polished binary builds for pushing forward these important changes to the broader Python community. Despite the progress, Python package management story was still far from a happy end. For truly reproducible builds, one component of the magical elixir was still missing: lock files. This is where Python had to learn from its competitor, Ruby. In 2009, a new tool was released that quickly became an essential part of any Ruby developer's stack. Bundler allowed you to write down your project's dependencies, gems as they are called in Ruby, along with the ranges of their acceptable versions in a file called gem file. This was really not very different from Python's requirements.txt. What was different is that when you installed your dependencies from a gem file, Bundler automatically created another file for you, gemfile.lock. This lock file listed the exact versions of everything Bundler just installed, packages you've put in the gem file, and their dependencies, which meant you could check in that lock file to your code repository and your teammates would be able to recreate your development environment from it, again, by using Bundler. Right now, some of you are probably thinking, come on, I can use my requirements.txt and then generate something like your requirements.lock with a pip freeze command. That is of course true, but as it often happens in practice, the devil is in the details. Sure, you can work your way maintaining a lock file with pip freeze, but this will demand, well, a considerable discipline. Always activate your virtualenv and only install packages required for your project there. No development packages like black or flake 8 please, and then always run pip freeze to reflect the changed state of reality of your virtualenv in a log file. What's more important, you have to know in the first place that your good old package manager pip supports this freeze command. You have to know how to use it properly, and to be honest, I haven't seen this practice becoming a standard in Python developers community. It just didn't stick. Python developer experience didn't change much with the introduction of pip freeze. Have you seen any mentions of log files management with pip freeze in any book or tutorial written for beginner Python developers? I've seen none. That's why in 2015 a new project was released, and it was the closest thing to the Ruby's bundler, but the Python way, of course. The project was called pip-tools, and it was actually two command line utilities that complemented each other. I personally still prefer pip-tools to its modern alternatives, all of them I'll show you in a while. I think pip-tools is the only Python package management related project that follows Unix philosophy. Write programs that do one thing and do it well, and then make those programs work together. Now let me show you how pip-tools solve the log file with virtualenvs problem. Not everyone in Python community was inspired by the pip-tools take on reproducible builds. In 2 years from its release in January 2017, a new contender on the package management arena appeared, pipenv. The author called it Python development workflow for humans. pipenv promised to make developers' life easier by providing just one command that would not only manage log files but also would try to install you a required version of a Python interpreter and create a virtualenv. Paying tribute to Ruby's bundler, the config file for pipenv was called pip file, and the produced log file pipfile.log. Interesting fact, up until 2021, pipenv used behind the scenes, a vendored version of pip-tools. To this day, the only tools recommended for log files management in the official Python packaging user guide are pip-tools and pipenv. Now let's have a closer look at pipenv. If you ask me, I would say the most important contribution pipenv did to improve Python packaging mass was not mimicking bundler, but trying to come up with a consistent development workflow and freeing developers from juggling shell one-liners like these. Fast forward to the present day, and I can clearly say that the idea of one single tool that manages everything, your virtualenv, your dependencies, and even development tools like linters, this idea is still afloat. What didn't stick is the pip file format. Well, sure, it's still in use by pipenv itself, but it's nowhere near to becoming a standard for storing a project configuration in the Python world. Instead, we now have the pyproject.toml format. Now, what if I tell you that pyproject.toml was in part aiming to fix one of the worst long persistent security backdoors in Python packaging infrastructure? Backdoor, in fact, so horrible you wouldn't even notice when your machine, a laptop, a CI/CD server, or maybe even your container image deployed to production is exploited. Do you remember setup tools? Yes, the one and only library used to make your own Python packages. The entry point for your package when you were using setup tools was the script setup.py. So if you needed, for example, to get a list of build dependencies for a package, you had to execute the script. If you needed to build a package from source, of course you had to execute the script. This is slow and non-deterministic, because who knows what kind of logic was put in setup.py. It's a usual Python script after all. You can easily run a random number generator there, for example. And of course, having setup.py means you need setup tools pre-installed. That's why you always have setup tools in a fresh virtualenv, by the way. All that makes setup.py an ideal backdoor, because just to get some metadata for a package that you maybe won't even install, your package manager potentially needs to run a script. It's like piping an output from a curl command to your bash shell, only much worse, because with piping, you at least know that some script from the internet will be now running on your machine. If your package manager, like pip, simply does its routine work and in the meantime executes some random code from the internet, again, just to get a piece of metadata, and of course you have no idea about this process. This is scary. In May 2016, PEP 518 finally proposed to replace setup.py script with a text file in TOML format, pyproject.toml, where build requirements for a package can be listed in a very straightforward way. While initially PyProject.toml aimed just to solve build dependencies and setup py problem, different community projects started using it as a settings file. In May 2017 it was Flit, a modern replacement of setup tools. Then, in December 2017, another can-do-it-all package manager appeared, and its configuration was entirely based on PyProject.toml. It was called Poetry, and it promised to configure and manage virtualenvs for you, while also providing a proper dependency resolver. You remember, Conda was the first package manager in Python ecosystem to try and tackle the dependencies resolver problem. Then pip-tools did it their own way, and pipenv piggybacked on the solver from pip-tools. Until November 2020, there was no dependencies solver really in the default package manager pip. And now Poetry's author also decided to solve the solver. Let's see what Poetry has in its sleeve. Although some folks try to demonstrate how good Poetry's dependency solver is by making it play Sudoku, and on YouTube you can now find bloggers saying that Poetry is a professional all-in-one project and dependencies management library and can really save your ass in a lot of situations.
Can really save your ass.
There are others openly expressing their frustration and even saying that Poetry is already outdated. The main complaint I see in people's comments on Reddit and elsewhere is that Poetry is slow. But is it really the Poetry's fail? Remember, when I talked about Conda's dependency solver, I said that there is no one right algorithm for this problem, and a package manager developer has to choose either to go the short path and just fail installation on any resolution conflict like pip did for a long time, or try to play that Sudoku, going over different packages combinations until it clicks. Remember why Python community settled on PyProject.toml as a replacement for setup.py. Have you noticed that on the PyPy website you can find no information on package dependencies? Now is the time to tell you the hard truth. Python dependency solvers will be slow, at least in the near future. And it doesn't matter if we are talking Poetry, pip, or a brand new thing written in Rust, as long as this tool will try to do its job without cheating, it's going to be slow. Here's the thing. Whatever package manager it will be, it needs to know dependencies for packages it's going to install. If the package you are interested in is fairly recent and popular, chances are to get its dependencies, it will be just enough to do a single HTTP query to reach PyPy's JSON API. This is how Ruby gems work. But if a package maintainer was not using the right tooling and has not provided a separate metadata file, in order to know just about anything about that package, it has to be downloaded and extracted. If there is no wheel matching your platform and your Python interpreter, then your package manager will download an sdist and then also execute a setup pipe from it. Why? I explained before. There are still lots and lots of packages that require you to execute setup.py to get any dependencies information. And of course, older versions of packages will remain as they are, probably forever. And packages relying on those older versions will still be triggering setup.py execution. And this is where the slowness of Python package managers comes from. In order to solve the versions constraint Sudoku, in many cases whole package archives and potentially many versions for the same library have to be downloaded. Therefore, the biggest bottleneck in building a LOCKFILE with the lucky combination of packages is not the solver algorithm, but your network bandwidth. By the way, Conda tried to solve this problem differently, the way your Linux system package manager does it, by generating beforehand a big-ass index file with all the required metadata for all the packages. This was possible because Conda started from scratch and used its own, completely independent from PyPy package repository. As you probably know, Poetry, although it became really popular in Python community, did not become a standard. And in just 2 years after Poetry's initial release, the first serious competitor appeared on the scene. The project name was much more prosaic, PDM. I guess it stands for Python Dependencies Manager, but I cannot prove it. The main idea behind PDM was to try to replicate the way projects are organized in Node.js. In Node.js, all of your project dependencies are contained in a project subdirectory called node modules. This is what PDM advocated for. Let's ditch virtualenvs because they are confusing, especially for beginners. Let's instead just have a special project subdirectory called .py packages, and let's make Python always add .py packages to the sys.path. There was a corresponding PEP, which, spoiler alert, was rejected later. Support for .py packages did not become a part of Python distribution, and now the latest version of PDM uses virtualenv, just like all the other package managers except for pip-tools. PDM just puts this virtualenv in the project directory by default. Yes, virtualenvs for sure are still confusing, and I do understand the original motivation behind PDM's creation. But to be fair, Python core developers are still working on addressing issues behind this crucial part of the development stack. And probably the most important recent change related to virtualenvs happened in May 2021, when PEP 668 was accepted. This change aimed to finally make shadowing packages, the problem which I explained before, impossible. The way the fix works is embarrassingly simple. If you try to pip install anything in a system-wide site packages location, you get a scary error message saying that you are trying to mess around with an externally managed environment, which basically means system-level Python packages are managed externally, not with pip, but with a distribution package manager like apt. If you still insist on installing globally, there is a special pip command line option with a telling name, break system packages. In order to label a Python installation an externally managed environment, Linux distribution developers have to place a special marker file in a predefined location. To my knowledge, latest Debian already adopted this approach. You can most likely expect there will be no externally managed environments in official Python Docker images, but in my opinion, you should still better use virtualenvs and restrain from installing Python packages globally, even in a Docker container. Because only a full virtualenv guarantees reproducibility for a Python project. As you already understand by now, the Python Package Manager's Battle Royale is ongoing, and the arena is full of contenders. A bunch of them are written in Rust, maybe following the success of Ruf, a really fast static code checker for Python. Right now, there are more competing package managers for Python than ever were, and I honestly think than ever will be. I'm going to demonstrate now the 5 most interesting of them, trying to compare them and of course paying attention to unique ideas each one of these package managers is presenting. If you are shopping for a new package manager or just trying to stay up to date, you will now see that almost all of these tools share the same user experience. Same commands, same virtualenv and optionally Python distribution management, similar project configuration files. Let me start with a modern redefinition of conda. If you are used to conda development workflow, or if you are going to work with scientific packages in Python, you should give it a try. Pixi uses a pixi.tomo project configuration file, can of course install conda packages, but contrary to conda itself, in Pixi there is no default global environments. Everything you install belongs to a project, which, if you ask me, is a good idea. Pixi is still in alpha, and its developers plan to add support for PyPy packages in version 1.0, which will make it the first package manager for Python supporting both package ecosystems. Rai, another package manager written in Rust, looks more like a well-designed wrapper for a bunch of already established Python tools. Like pixi, it manages Python interpreter installation. For configuration, it relies on the standard pip-project.toml, ships with rough, and uses good old pip-tools, or a newer container UV, to actually install packages and resolve dependencies. Rai is the only package manager that tries to provide a good workflow for Python mono repos. This is what it calls workspaces. Next one is called Hatch. This project is hosted on GitHub's PIP organization, neighboring with pip, setup tools, and wheel repositories. Hatch is written in Python, so there is no copy one binary installation option, but you can use pip-x. Pip-x, by the way, is a special utility that allows you to install Python tools that you want to share between different development projects, just like Hatch or maybe like Bandit or Pylint. Hatch follows a different path to all the other package managers I know, in that there is no install command. This was confusing to me when I tested Hatch, and apparently is confusing to other people as well. In order to get your dependencies in your virtualenv, yes, here Hatch is not different from the crowd, it manages your virtualenvs. So in order to get dependencies, you need to start using your virtualenv by issuing a run or a shell command. This will sync virtualenv with whatever is configured in pip-project.toml. Doesn't look too nice for Docker deployments though. Anyway, for dependencies solving, Hatch uses plain pip. Interesting idea that is unique to Hatch and that may be useful for those of you who need to test your code on many different Python versions is called matrices. If you thought of CI build matrices, yes, it seems to be something like that. Hatch is considered experimental by its author. One more experimental package manager, huak, is written in Rust, inspired by Cargo, Rust package manager, and is supposed to be installed with Cargo, which is a little bit too rusty to my taste. Huak uses pip to install packages, bundles a formatter and a linter, and manages Python distributions. However, I was not able to figure out how from the get-go. Last but not least, a package manager that considers speed its main feature. My very simplistic crash test that I've done with all the package managers in this review does confirm that only pixi, which is conda based and therefore not constrained by the PyPy problems I've discussed earlier, is even faster. Compared to plain pip, UV is roughly 10 times faster, which to my understanding is achieved by solving the dependencies Sudoku faster with Rust, and also by utilizing download bandwidth much better. Latest pip still downloads packages one by one, which contributes to its horrible performance when you install, for example, serious machine learning packages. But back to UV. Notable UX feature of UV is that it tries to replicate command names from pip and pip-tools. So the idea is that you can replace pip or pip compile calls in your scripts or Docker files with something like UV pip install, UV pip compile, and UV pip sync. So you basically just prepend your commands with UV. Just like with pip-tools, a log file generated with UV is platform specific. So if you work on a Mac and want to deploy to AWS Lambda, run UV pip compile in a Docker container. Interesting command line option that is also available in PDM, exclude newer, will filter out all packages newer than a given date. Could be an amazing time saver in a situation when you know that a recent update of some of your dependencies broke your project's environment. Now that you know how Python packaging developed over time, what challenges it faced and still has to overcome, with an overview of all the interesting tools available today, I can go on with the most down-to-earth, practical part of this episode. My package management advices, all of them backed by experience. If you jump to this section just to get to the practical advices on Python packaging and you don't care for the reasons behind them, which I explain in this video, that's fine. Let's start. First, Do not use a Python interpreter installed with your operating system. Use a tool like ASDF, or if your package manager of choice manages Python installation, go for it. Make sure your newly installed Python interpreter is used by default when you are working on your project. If you use pip, call it with python-m pip to be absolutely sure you are using pip from your separately managed Python installation. Check that Python version you've installed matches the version you use in production. Second, whenever you start working on a Python project, even if you think that it's going to be a small thing, always start with a virtualenv. Use a VENV module from the standard library to create one. Again, be sure to create a virtualenv using a Python interpreter you installed separately. Do not use a system one. Most of the package managers I presented in my video handle virtualenv creation for you. Third, use a LOCKFILE for your project dependencies. It doesn't matter much which tool you will use to create a LOCKFILE. I personally prefer pip-tools and most likely will give a try to UV soon. But if you or your team likes Poetry, PDM or anything else, just stick with it. For pip-tools, remember that it creates a platform-specific LOCKFILE, so if you say develop on a Mac and want to deploy to AWS Lambda, use Docker to run pip compile in a Linux environment. Let me stress that once more. Do not rely on requirements.txt with a list of package names you need for your project. Be sure to commit and push your LOCKFILE to your code repository. Fourth, if your package manager is stuck for a very long time, check its logs. Make a note downloading or checking which package takes most of your package manager's efforts, and then try to pin that package with a greater recall version operator. Take into account that different package managers, even though they may be using the same pyproject.toml file for configuration, may use different syntax for version constraints operators, and even different strategies for package constraints. PDM, for example, puts a greater recall version constraint operator by default when you add a package to pyproject.toml, which is quite easy to understand. It means that on the next upgrade, PDM will try to find any suitable newer version. Poetry, however, adds a so-called caret pinning operator from the Node.js world. Caret pinning limits possible upgrade candidates with regards to semantic versioning. If you are using Poetry, do check Poetry documentation to understand how it works in details. By the way, some people in Python community think that caret pinning brings more problems than benefits. Just for you to know. Fifth, to deploy your project, regardless whether in a container or not, deploy a virtualenv. Do not just pip install packages for your project using system pip. To activate your virtualenv in production, you only need to set these two environment variables really. Set them in your Docker file if you deploy your application using containers, or in a systemd unit file if you deploy on VMs. That's it. Here's an example Docker file. Sixth, if you develop a library, use modern tools like Flit to package and publish your creation. Stay away from setup tools and setup.py based configuration. And finally, Python ecosystem is big, with different parts of it having different needs and different value propositions for the rest of community. Python packaging, as a result, developed in waves, trying to absorb the ideas from different parts of community at the same time being careful to resist breaking changes. Today, package management is a commodity which has its benefits and downsides. Please be respectful for the work of thousands of developers, package maintainers and tools developers. I explained in this video that they almost try to do the impossible. Be also extremely conscious of what you're using. Don't depend on random libraries that you got to know just today in your production code. Remember about supply chain attacks, it's not a joke. Thank you for listening. I've spent a lot of time and effort to prepare this episode, so if you find it useful, I kindly ask you to share a link to this video with your friends and colleagues. See you next time, good people!